Hey everyone, this is Brian, recording another video lecture for CSC 143. In today's video, we're going to be covering several popular linked list algorithms. If you haven't had a chance to download the notes from last class and investigate the source code, I highly recommend you do that now, because in today's lecture, we're going to be covering that source code and talking about how we can extend it to implement several of these interesting algorithms. Linked lists provide several interesting algorithmic opportunities, which are implemented quite differently than those with array lists. We learned about how linked lists involve a lot of reference chaining, whereas the array list is simpler to work with because it's just a bunch of contiguously stored values back to back. As it turns out, linked list manipulation problems are commonly found as technical interview questions because they require a deep understanding of how references behave and how data structures are arranged. As an exercise for today's lecture, we're going to be writing a lot of these algorithms together. And as an added challenge for yourself, I really recommend whipping out some pencil and paper so that you can see if you can come up with these algorithms on your own without external assistance. Now, of course, you can't just sit through this whole video and get all the solutions immediately, but I do recommend that you pause from time to time to think about what you would do if you were presented with such a problem, and think about how you would go about solving that problem with the methods that we've learned so far. Let's go visit LinkedList.java and dive in. When we start out at the top of our file, we see the same linked list shell that we had built out from last time. The linked list class is a generic class that implements the iterable interface, telling the world that the linked list can be iterated over. It manages a head reference and a tail reference that point to the head nodes and the tail nodes of the list respectively, as well as an internal size property that keeps track of all the insertions and removals that happen. Recall that the linked list has two constructors that we've defined for it, a default constructor that sets the head and tail to null and the size to 0 as an initialization for an empty list, and the second constructor here, which takes an iterable as an argument, where that iterable can be any class that fulfills the iterable type, including linked list, array list, set, and so forth. We're going to build a linked list from that iterable type by using the for each loop to pull individual values outside of the iterable, and build the list in the same order as which we were iterating over the items inside that list. If you scroll down a little bit, you'll see a new function that I've added to this linked list source code called copy. If we read out the method signature, we see that copy is a method that returns a new linked list of t, but this time it's a static method, so I can actually invoke the copy method on the definition of the linked list. What this copy method is going to do, as you can infer, is it's going to build a new linked list from an existing linked list. The nice thing about copy is that I can effectively do the same thing as building that linked list by hand, but I'll actually use the convenience of that iterable constructor that I had already written. Remember that linked list itself is an iterable, which means I can pass linked list to the linked list of iterable constructor. So one way I can get a copy, value by value, of an existing linked list is to just call that linked list constructor that takes an iterable type. This is kind of the magic of interfaces and abstraction at work, is that, as usual, Java doesn't care what class fulfills the interface so long as it actually has a method implementation for all those method declarations. So I can just use a little bit of syntax magic, call my own constructor inside the class, inside the static method here, and get a nice factory method that clones linked lists without any additional work. Down here I've got some methods push front and push back. Push front appends elements to the front. I only have two cases to consider. Either the list is empty, in which case the head and the tail become the same new node, or the list has elements inside, in which case I create a new node that becomes the new head. Push back is the same story. I have two cases. Either the list is empty or it's not. If the list is empty, the head and the tail become the same node. If it's not empty, I have a new back node that the tail is going to point to and then become. I've got the size method down here that returns the size field, which is an O of 1 operation, so I don't have to walk the entire list to figure out its size. And then, by nature of the linked list itself being an iterable, I need to provide an iterator that external clients can use to walk the elements inside the list. Here, that class is going to be the linked list iterator class, which is a nested class within the linked list. Remember that the iterator is obligated to provide a next and a hasNext method, where next pulls values outside of the linked list such that the clients can read them and moves the pointer forward to the next element. And then hasNext is a conditional check that determines whether or not there's elements remaining. The way I'm going to build my linked list iterator is I'll take a node reference and have that be the first value that gets returned. And then as I call next over and over again, I'm going to move that reference forward to the next node, and the next node, so forth, until eventually that head reference inside the iterator becomes null. Then down here, inside my linked list class, I have this iterator method, which the iterable classes are obligated to fulfill, that returns an iterator type. That is, of course, this linked list iterator that we just defined, and will pass in the head node that we provided inside the outer class. Okay, so that's all a big summary of the things that we did last time. And before we move on, I really want you to have a firm understanding of how this linked list is constructed and how we worked on these methods like append front, append back, and this linked list iterator. So again, before we move on, I do recommend you pull down these notes, you walk through it by hand, maybe try debugging some of the tests from last lecture's code so you can really understand what the nodes are doing within the list as we manipulate it. All right, for our first interesting algorithm, let's try equals. Remember that the equals algorithm is responsible for determining value-wise if two objects are the same. This is different from just reference equality, which we've seen with a double equals operator that just asks if two values are physically at the same location in memory. There's, of course, always going to be instances where we have two different standalone instances of a class, and those standalone instances happen to be equal semantically, but they live in two different locations in memory. This linked list equals method is going to determine if two lists are exactly the same based on the values within the list, but not necessarily the same in terms of references. With the equals method, you can imagine that we'll follow a very similar pattern to all the other equals implementations that we've done in the past, where we have something like a null check, a self check, a cast check, and so forth. But this is the first time that we've seen a data structure that has multiple elements be compared to another data structure that has multiple elements. Go ahead and pause this video, take a moment to think about what you would have to do to compare one linked list to another, and then when you're ready, go ahead and resume and we'll talk about the solution. Okay, I hope you've had a chance to think about it. Let's go over what I would do for a linked list equals implementation. We'll start out with the basic checks. We'll check to see if the list is null. If that's the case, then we immediately return false, of course, because we know that the instance that we're invoking this method on, is not null. If we happen to have reference equality using the double equals operator, we can take an early exit and return true, because it means that the object being passed in is physically the same object as the object that we currently live on. If the two instances have different classes, then of course they're not going to line up. The method signature of equals says we can take an object as an argument, so technically the O instance can be of any type. We have to validate that it is indeed a linked list type. Also remember the difference between the getClass method and the instance of keyword that enables classes to be equal to their child classes. Here, linked list doesn't live in a class hierarchy, so it doesn't really matter that much, so I've chosen to use getClass. Next up, I perform the cast. Another quick way to validate whether or not two lists or structures are the same is to actually check their sizes first. This is one of those easy exits because this is again an O of 1 operation. The size method on both these lists is going to be O of 1, and if they have different sizes, then I don't need to go about comparing their internal values, and I can immediately return false. Okay, now for the meat of the equals implementation. I need to go about comparing all the values between the two lists index by index. So the first two elements of the list should be the same, the next elements of both lists should be the same, the third elements of both lists should be the same, all the way up into the tail of both lists. And we know by this point, after we've passed this guard statement on 1112, or on 112, that the lists have the exact same number of nodes. So we should be able to iterate over both lists simultaneously and not worry about one list being longer than the other. I'll start out by getting an iterator out of both lists. Now you may be tempted to start writing a for each loop here, which you can also do. But the nice thing about pulling out the iterators manually is that I can also invoke the next method on both at the same time. If I use a for each loop, then I'll still have to have an iterator of the other list, because I can't have a for each loop iterate at the same pace as another for each loop, since they'll run independently. So to be explicit, let's go ahead and call the iterator method on both lists to pull out an iterator. Then what we'll do is start to loop through all the elements. Remember that we know that both lists now have the same number of nodes. So while I can still iterate over the iterator, if the first iterator's value, that is the iterator that is for this present list, if the first value for that iterator is equal to the first value of the next iterator, then I know I'm good. If that's not the case, I immediately return false, because I've found two elements within the list that are in the same position in both lists, but are not equal to one another. Once I finish that check, I go back to the top of the loop. I ask if there's more values to iterate over. If so, I'll check those values. The second call to next pulls out the second value within the current list, and the second call to next for the other iterator is going to pull out the second value within the other list. And if those things are not equal, then I found two elements in the same position in both lists that are not equal to one another, and then I can return false right away. I'll keep doing this over and over again until I've eventually exhausted all the elements across both lists. Again, we know that both lists are going to be the same length. Once hasNext returns false on one iterator, then hasNext should return false on the other iterator as well. And if I passed all those guard statements that check if all the values in the same positions in both lists are equal to one another, then I can finish out by returning true. So that's my implementation of equals. And your implementation might have been a little different. You may have been tempted to write that for each loop, which is something you can do. Let's go ahead and see what happens if we try to do that. Suppose for a moment that we were iterating through the current values of this list and comparing them to the values of the other list. I might do something like for t current of iterator, this. I need to compare them against the values of the other, I need to compare them against the values of the other iterator. Now the annoying thing here is that I can't write a loop within this loop and do that, because I've pulled out one value from this outer for loop, but I'm going to end up pulling all the values inside this inner for loop to finish execution of this for each loop. So I do actually need this iterator here. At the very least, writing the for each loop eliminates the need to make this first iterator, because I'm already doing it implicitly with the for each loop. What I can do is, remember, assuming that both lists are the same length at this point, which isn't an assumption anymore, we know it's going to be true, then we can start pulling out values that are from the other iterator and comparing them to the values in the current iteration. We might ask if current is currently not equals to other iterators next, then return false. In effect, this is going to do the same thing as what we did with this while loop down here. Remember that the for each loop is really just syntax sugar for declaring an iterator manually and then calling the next method until the hasNext method returns false. So I hope you were able to come up with a solution that looked kind of like this. With these data structures, we do have to have a bit more complexity in our equals implementations, because we don't just get to compare the internal state fields of the two classes, but we have to go about comparing all the other referenced items from the class's perspective. One nice thing about these notes that I'm posting for you today is that I actually provide a test suite for all these algorithms. So if you'd like to update these notes on your own time and see if you can come up with these implementations on your own, you can actually run them as if you were working on this in a project. Let's check out this linked list equals test. I start out with two linked lists A and B, and I assert that A equals A and A equals B. Both lists are empty, they should equal one another. Then I also verify that the string C is not going to be equal. Next I push the lowercase a and the lowercase b to A and B respectively, and I see that the two lists are no longer the same. Then I go ahead and push B onto the back of A, such that list A has AB inside, and then I push lowercase a to the front of B, such that list B also has AB inside, and I see now that they're equal to one another. I push C to the back of A, and I see it's no longer the case that they're equal. And finally I push C to the back of B, and I see this should be equal to one another once again. Let's go ahead and run that test to make sure our implementation still works. Great. Next up in our list of algorithm challenges for linked list is the clear method. The clear method should delete all the elements of the linked list such that the internal state of the list becomes empty after it's being called. This one's actually quite trivially simple in a garbage collected language, so take a moment to think about it on your own, and when you're ready, let's talk about the solution. Okay, hope you're ready. You might be surprised to see that the solution is just 3 lines long. In our clear implementation, all we do is assign head to null, assign tail to null, and assign size to be 0. This clears the linked list because it makes it so that there are no more additional references that will point to all the nodes within the list. Java is a garbage collected language, which means it's automatically going to free memory of instances that are no longer referenced to. It does this through a strategy called reference counting, which essentially tracks how many references exist to every live object in memory. As soon as that count goes down to 0, Java knows that there's no possible way to get back to that object, and so it's going to free that piece of memory. Here what we do, by nulling out the head and the tail, is we eliminate the head and the tail references, so whatever nodes were there previously, if any, are gone and no longer referred to. Then all the chained nodes together that actually make up the list itself, well, they reference one another, but there's no way to actually reference the underlying structure as a whole. So those nodes should be garbage collected as well. Now, you might be thinking, well, what if there actually was another reference to those nodes that we just don't know about? And that is indeed a possibility. It could be possible that there is another linked list out there that for some odd reason, we've perhaps written a method or some code that we didn't know about that actually assigned the head and the tail nodes to be the same as an existing linked list. The scary thing about that kind of pattern is it means that other linked lists could technically manipulate other linked lists without them knowing about it, such that if you append to one linked list, using push front for example, it'll affect the other linked list without that other linked list being updated. We're going to avoid having that problem by declaring these variables to be private. By saying these variables are private, we're essentially telling the world, I'm not going to give you access to these references and these underlying properties. Private is very much a form of encapsulation. By preventing external clients from ever being able to directly read and write head and tail, we avoid this issue of extraneous references to these head and tail nodes that would otherwise prevent them from being garbage collected. Now, this does not prevent us from falling into a trap of still writing a method inside the linked list that would cause additional references to head and tail to be created. For example, for a moment, let's suppose we were trying to write this copy method in a naive way. And what we did was, rather than iterating over all the values within the linked list to be copied and copying those into a brand new linked list, we actually just referenced the same head and tail nodes as that existing linked list was referencing. The outcome is that we're going to have two linked lists that follow the same underlying structure. And then we have this issue that we just talked about of how one linked list methods are going to update that linked list but not be reflected in the other linked list state. So if we try to push front to the original linked list, both lists will have one additional element, but only the original linked list will have its size incremented. We end up in this weird state where the list itself doesn't have proper integrity underneath and doesn't accurately reflect the state of the object. So we do have to be careful in Java to make sure that these classes that we build have well-defined management policies of their references. It should be very clear that these instances are going to manage their own references and not offer these references up to other classes. If we had made these public accessible references, then it could be possible that another client could come in and rewrite the head or the tail or copy the head and the tail in a way that we don't expect. So here these access modifiers are really putting encapsulation at work for us, and it's a pattern that we want to continue to follow to minimize possible exposure and avoid these little traps. Anyway, I hope that's enough to demonstrate why the clear method in this language makes sense to you. In some other languages that don't have the convenience of garbage collection like C or C++, it may not be so simple as to just assign the references to be null. In C, which is a manually memory managed language, say that 3 times fast, we have to explicitly allocate and deallocate memory with specific calls to system functions. If we fail to deallocate all the nodes in between head and tail, then we get a memory leak, because there will be several nodes in the list that are still live in memory, but can no longer ever be accessible. That's something to think about if you're ever doing some low-level language programming, where you have environments that have very strict policies about how memory gets managed. In Java, it's going to be abstracted away to us, which is why we get this very convenient solution. But this is something that I do want you to consider, especially if you ever asked this during an interview. In terms of the language, you may have either a very simple implementation, like the Java implementation, or a more complex one, like for C, where you're going to have to go and manually free and delete all the instances of the list itself. Okay, moving on, let's talk about this next method I'd like you to write, the join method. This method is going to join 2 linked lists together. And in this example, I'd like you to destroy the list being passed as an argument. What I mean by that is I'd like you to actually absorb the nodes being passed to the other list and essentially clear out the other list. So this is kind of like there being 2 trains on different tracks. You can think of a train as kind of a linked list where each cart is a node inside the list, and I'd like you to join the 2 trains together. So the outcome of that is you'll have a big train that is composed of all the carts combined, but the notion of there being 2 separate trains is going to stop existing. The second train just becomes empty. There's nothing there anymore. Take a moment to think about what you'd have to do for the join method implementation, and when you're ready, come back to the video and we'll talk about the solution. Okay, I hope you've had a chance to think about it. Let's talk about the solution for the join method. I think we're going to base our observation on the fact that linked lists are really just independent nodes linked together, hence they're linked lists. And with that in mind, it doesn't really matter which node is the head node or which node is the tail node, so long as the list is consistent about it and says, this is going to be the head links to several other nodes, and this is going to be the tail. We could technically reassign the tail to a different node in the middle, and external clients of the list would still see it as a complete linked list. So with that in mind, when we accept this other linked list argument here and we want to absorb the nodes of that list, we can essentially attach the head node of that other list being passed in to the tail node of our current list, such that that head node that we just stole from the other list is going to be the continuation of our existing list. Then this other list's tail, the very last cart of the train of the other train, is going to be the new last node, the new tail of this current list. Let's walk ourselves through how we would do that. Let's start out with some basic guard statement checks. It is possible that the other list is null. This is kind of an annoying thing in Java, is that you could technically have a null reference anywhere there's a reference to be expected. So do double check that. There are some languages where it's very explicit whether or not something can be nullable, but in Java, everything is nullable potentially. So you do want to do a null check. If that's the case, immediately return because the other list is effectively empty. If the other list size is also 0, then we can also return because the other list doesn't really exist. The head and tail should be expected to be null in those cases, and there's no other elements to append to an existing list. what about the case where this existing list is empty? If this list is empty, then if we're trying to join an existing list that does have elements, we need to essentially absorb all the elements and nodes within that other list and reset that other list. So here we steal the other list's head, we steal the other list's tail, we steal the other list's size, and we clear out the other list. Now this is an example of one of those methods where you could fall into this trap of having two different class instances that manage the same underlying structures. We talked about this when we went over this clear implementation and how this could potentially be dangerous in causing a memory leak if we weren't confident that assigning these to null eliminated the last reference to these nodes inside the list. Here, for example, if I forget to call clear on the other list, then we're going to have two live instances of linked list that manage the same underlying elements. However, it's possible that they will become inconsistent over time when methods are called in one list and not the other. Again, if I try to append to one of the lists, the node changes will reflect in that list only and not the other list, because the tail or the head might not get updated and the size isn't going to get updated either. So we have to be very careful about when we access the raw data references inside other instances of our own class. I would say this is a special occasion. We just have to be careful to, reset the other list when this happens to make it obvious that the other list is no longer to be managing these individual nodes. Okay, once we pass all these checks, we only have one case left to consider, which is that both lists are non-empty and we need to join two lists together. Here's how I'll do it. I'll chain together the head of the other list to my existing list tail so that it continues on and my list grows bigger. Then I'll set this list tail to be the current tail of the other list, because the current tail of the other list is the last node of the other list. And if I'm joining them together, then my head stays the same and my tail is going to be this last node of the two lists combined, the last node of the other list. My size, of course, also increments by the size of the other list. And finally, don't forget, call this clear method so that you explicitly tell the world that the other linked list instance is no longer going to be managing these nodes. Okay, hopefully that wasn't too much to digest. I do recommend that you think about these kinds of problems in these kinds of individual breakout cases. We kind of followed a similar pattern when we wrote equals, where we got past a bunch of assumptions about the object being passed in, and during the meat of our implementation, we were assured about all those assumptions being true, that it wasn't null, it wasn't ourselves, and it was indeed the same class. When it comes to a lot of practical programming, you'll be needing to do the same thing, is having these precondition checks just in case, and in case there's also easy exits. And then finally, when you've passed all those precondition checks, you can finally get to the meat of the implementation. Next up in our series of linked list challenges is the reverse method. Reversing a linked list is another one of those stereotypical technical interview questions that comes up a lot. In this case, we're reversing a singly linked list, so we essentially need to make the list tail be the new head and the list head be the new tail. But what's also challenging is having to reverse the pointers within. You need to somehow make all the list nodes point to their predecessor, which may not be immediately accessible, rather than their successor. Take a moment to think about the reverse method, write down a solution, or a draft of a solution if you can, and when you're ready, get back to the video and we'll talk about the solution. Okay, so this method is a bit more complicated than the other ones we've seen so far, because it involves a decent amount of forethought into how pointers get managed inside the list. And I want to actually turn to the whiteboard for a second to discuss the base cases and the bigger case that we have to deal with when solving this problem. Suppose for a moment that we had an empty or a single node linked list, a linked list with just one element. The list itself is already reversed, the head and the tail are the same, and rotating that amount doesn't have an effect. Now how about a list with two elements? If I start out with the list in black ink, where this head node points to the tail node, then what I have to do is effectively swap the head and the tail, and then set up the tail such that it points back to the head and null out the next reference of the head. That's how we deal with it in the case where there's 2 nodes in the linked list. Now for the general case where we have 3 or more nodes in the linked list, it's a bit more challenging. We have a head node and a tail node which is located arbitrarily far away. We know the head node has to be nulled out, or at least the head node has to point to its predecessor, which isn't currently null because there's nothing before the head node. The head node's successor has to point back to the head, but if we walk the list and just have one reference to the head and have this next node be the new head, then we actually lose access to this previous node. So we have to keep track of this original previous node with an additional reference. Next up, suppose we wire up the second node in our list to point back to the previous node, which we kept a hold of. Then we also lose access to the node that comes after the current node that we're working on. So we actually do have to keep a third reference here, which is a reference to the successor element to the node that we're currently working with. This 3 reference window is what's going to get us to the solution of this problem. We have to start with this second node, which I'll call current, wire it up to the previous node, and then move all the pointers forward by 1 node, which we track via this next reference. So in order of operations, we start it with the head, we assign heads previous to be null, we assign heads next to be this current reference, and we set up a loop as follows. The current reference is going to point back to the previous reference, but before we do that, let's go ahead and save the next of current so that we can get back to it later. Then when we're done wiring up the current reference to point to the previous reference, we move our 3 references forward by 1 node. We know that's possible because we can replace current with next, and we can replace previous with current. And so long as we still have access to next, we can go look at next successor as well, which we should go do first. Anyway, we end up moving all these 3 references forwards, and then we get a new set of current, previous, and next nodes. We, once again, save the next node, which we should have already done, because we moved the next node forward. We assign the current node to point back to the previous node, rather than its existing successor. And then we shift all 3 nodes forwards. All 3 references, that is. Once again, we follow the same process. We make sure to save whatever successor to current is inside next, which is actually null in this case. We wire up current's successor to point back to the previous node, and then we shift all the references forward one more time. The final outcome, is that the current reference is eventually going to become null, and that's when we know we've processed all the nodes inside the list. So the tough thing about this solution is that it requires us to actually keep track of all these references, and it's not immediately intuitive that you have to keep track of 3 of them. In the case of a doubly linked list, for example, which we'll talk about pretty soon, it would be easier for us to get access to a predecessor node from a given node. But in this case, since we're working with a singly linked list, we don't have that convenience. If we move our references forward by 1, we have to keep track of the previous reference. Similarly, if we replace that reference that succeeds the current node, we have to keep track of that original successor in case we need to use it again. Now let's talk about how we implement this in code. I'll start out with some basic precondition checks, like if I have a list that has a size less than or equal to 1, I'll just return immediately because I don't have to do anything. Then I'll go ahead and set up my 3-pointer window. I'll start out previous as head, current as head's successor, and next as head's successor's successor. You might be wondering if there's the possibility of a null pointer here. We should be safe if the size is at least 2. If we pass this check, we know the size is at least 2. Therefore, we know there is a head and there is a head.next. The head.next.next may be null though, but we haven't actually done a lookup on a null field, so that's okay. Our very first step is to assign head.next to be null, because head's going to be in the tail, so it should point to nothing. We'll also go ahead and save the original head of the list, because that needs to become the tail of the list. And we'll go ahead and swap that with the tail right now. This is a step that I forgot to mention in the whiteboard, so apologies for that, but it is something we have to do to maintain the structure of the list itself. Okay, so once we get all this overhead work done, now we can start looping through the elements and rewiring the pointers. Remember, the procedure is to wire up the current reference to point back to the previous node, and then move all the pointers forward, such that next becomes its own successor, current becomes what was next, and previous becomes what was current. We finish reversing the linked list when the current reference becomes null, so there's no more nodes to point back to the predecessors. How do we do that? Well, let's do it this way. We'll have next be current successor, which it should actually start out as. We'll rewire up the current successor to point back to its previous node. Then we'll set up the previous node to move forward by 1 by pointing it to be, by setting it to equal to the current node. And then we'll set up the current node to be what the next node is. Then when we reach the top of the loop again, the next node is going to save current next, which is the successor of current, and the pattern repeats until eventually we've moved the current reference forward to the point where we've reached the end of the list and we're done. So there is a lot to observe and absorb here. I don't expect you to come up with a solution to reverse right away, but it is something that I think is important to think about, because it's one of those problems that when solving it, you kind of discover and unpack the solution over time, even though it's not intuitive right away. We learned how we will have to rewire a node's successor reference to point to its predecessor. But in order to keep track of the predecessor, we have to have an additional reference to do it. For a node to have a predecessor, we need effectively 2 nodes at least, so we should have this precondition check. And then if we have at least 2 nodes, then we can manage 2 references. But then, when we try to rewire the current node successor to point to its predecessor, we lose access to the current node's previous successor. And we need to keep track of that in yet another reference that's added in our algorithm. Fortunately, that's all the references we'll be needing. And then the final tough thing is figuring out when to stop executing this algorithm of reassigning these references and moving the window forward. Eventually, in the case of this reverse the linked list problem, we're going to hit a point where there is no more node to rewire. We know we've reached that point when the node that we are targeting that is up for modification, this current node here, has effectively gone beyond the tail. The outcome of that is that this previous reference becomes the tail, and the tail has no successor because current ended up to be null. So there's no more work to be done. The previous node should already be pointing back. The previous reference, that is, should be pointing back to its predecessor and so forth. Finally, don't forget, you do have to set up the class to work, the class references head and tail to work out. So that is a step that you should do. Of course, the size of the list does not change after you reverse it. So that's not something that has to be updated. As an added exercise, again, remember that there is a test suite included in these notes. So if you want to tackle these problems as if you were being challenged them on the spot, then I do recommend you clear out these implementations and give it a try on your own and run it against the test to see how it works out. Let's actually go visit those now, just to be sure. We'll go over this join test real quick because we haven't gone over it yet. Suppose we have 2 lists A and B. If I join A and B, oops, let me go ahead and word wrap here so we can see the whole thing. We'll start out with A and B as 1, 2, 3, and 4, 5, 6, respectively. Then when I join A to B, I should expect those 2 lists to be combined. And iterating over the values of A, I should get all the values of the list 2 combined. Then down here for reverse, I come with a list of 1, 2, and 3. I invoke the reverse method, which reverses the list in place. And then upon iterating over the values of the list, I get the list values in backwards order. Okay, very last challenge of the linked list algorithms challenge is this insert method. As you can expect from the method signature, what it's going to do is it's going to try to insert a new node with the value payload at the index, such that it becomes the new index and all successors of the index have to get shifted over by 1. I'll give you a moment to think about this one, and then we'll talk about the solution. All right, for the index method, you can kind of think about how we have to reach the index that we're looking for, and then update the node in place, or replace the current node at the index, and shift over all the existing references to existing nodes by 1 index. The shift over process isn't too hard, right? If we're going to come up with a new node to insert this value with, then to shift over all the existing values is just a matter of wiring up the existing values to the next reference of the new node we're adding. However, we also have to keep in mind that the existing previous nodes of the list do have to reference this new node, so we have to be conscious of that. We'll start out by building a new node that's going to get inserted. If for some reason the index being passed in is greater than the size, or the index is less than 0, then we throw this new index out of bounds exception. It is okay for somebody to call insert on the size as an index. This is just a fancy way of inserting to the very end of the list. Even though the list is 0 indexed, if you specify the index that is 1 beyond the last index, the client is essentially saying please insert to the very end. Similarly, if the index happens to be 0, this is the same thing as push front, which is a method we've already implemented, so we're going to just call it right away. On the flip side, if index is equal to the size exactly, then we can call push back and return right away. Otherwise, we have to do the work ourselves. Just like with the reverse example, we have to think about what references we need to hold on to so we can use them later and we won't lose access to them during the insertion process. What I'll do in this case is I'll have a previous and a current. And remember, we need to be also conscious of null pointer exceptions. If this.head happens to be null, then the list is empty. In which case, I should only ever expect index to be 0, so I can just go ahead and call push front. So there should be at least one index, or there should be at least be one element inside the list at this point, so head should not be empty, but head.next could be empty. We need to start looping through all the indices inside the list, and we'll do it with this while loop here, which is just going to increment this index I. And what I'll do is I'll shift our pointers forwards until I reach the point where I does indeed equal the index. Thanks to these precondition checks, where we check to see if the index is valid, we know that we should hopefully not ever hit a null pointer exception where we look beyond the end of the list. So here current could be null, but we know that I is indexing something legitimate. And at the very least, I should start out as either exactly the index we're trying to insert into, which is 1, and current is null, so we'll just insert into there right away, or current is the index of 1, and we need to eventually reach that by incrementing I to hit our target index. So what will we do? We'll move our current reference forwards and increment I, but we'll also hold on to the previous reference because we'll be needing it soon. We have to wire up the previous to point to this new node that we're inserting. Walking this list should be pretty comfortable to you. Again, this is just a matter of updating the reference over and over again until we reach the ith node inside the list. It's a bit easier to think about if you don't think about the previous reference first. Current is just the first element, current is the node at index 1 in our list. The head is the node at index 0. And we want to set up current such that it becomes the index that we're looking for. But with a little forethought, we can also realize that we do need access to the previous node, the node that comes before current. So we'll go ahead and make a pointer that just keeps track of that as we iterate over the list. Then finally, when current lines up to be the index that we're targeting, we need to wire up the previous node to point to this new node that we're adding, because this new node we're adding is going to take the spot of that index we're targeting. And then that new node we're adding is going to point to the remainder of the list, such that the remainder of the list essentially gets shifted over by one index. I would say this problem is a little bit easier than the reverse problem because it doesn't require that much pointer manipulation, but the iteration process is something that may initially be not so comfortable. I've had a lot of students who struggled during exams to write this loop because it's a bit more complicated to think about than just indexing in an array, for example, where you can just quickly use bracket notation to get to the value that you're looking for. Here, because we have to walk different node references, we do have to set up a reference at a particular index and then fast forward that reference until it reaches the index we're looking for. This on its own isn't really that much more sophisticated than a for loop. It's just the syntax is a little bit more weird, I suppose. You have to still, well, I guess it could be a for loop if we just have this as the increment and have this as our condition and has this as our initializer. So it's about the same. In fact, it is the same. But you should be comfortable with understanding how this next reference itself is a reference and it replaces the reference that is current until current points to the node at the ith index. Okay, let's go see how this works inside the test, linked list test. The linked list insert test is going to start out with a linked list of A as the values of 1, 2, and 3. Then when I insert at index 0, I should expect that 0 becomes the first element that I iterate over during iteration. I should also see that the list size has become 4. Why don't we just go ahead and add that assertion? Similarly over here, if I choose to insert at the index that is equal to the size, then I should actually get the behavior of appending to the back of the list. So 0, 1, 2, 3, and 4 become the new list. Then over here, if I try to insert into the middle of the list, that should indeed take the spot of the index I'm targeting. So 0 and 1 are the first two values I encounter, and then this new 1.5 shows up at the second index in the list. Then the remaining values 2, 3, and 4 will appear. In this last case, I try to insert into an index that is way beyond the end of the list, and I should see that this should throw an index out of bounds exception. Fantastic. Okay, so that's all the exercises that I've had for today about the linked list. You can certainly expect more linked list algorithms to appear in upcoming projects and exams. Your next project is going to be a doubly linked list where you'll get to implement a lot of interesting algorithms, but this time with previous references in addition to next references. In some ways, the algorithms will be a little bit easier because you don't have to keep track of additional references during the algorithm. However, in some cases, the algorithm will be more difficult because there are more references that need to be internally updated to update the state of the list. Again, I recommend that you download these notes, you try and fill out the body of these method implementations on your own, and you run the test cases against them. Alright, so that's what we've got for linked list algorithms, and now I'd like to talk about two new structures that are easily built atop of the linked list. These structures are the stack and the queue. The thing I like about these two structures is that it's not so much about how we organize the data underneath within each structure, but about how we access the data being stored in the structures. Let me explain what I mean. A stack is a data structure which mimics a stack of items in real life. It's going to have the following operations: push, that inserts an element at the top of the stack; pop, that returns and removes the element on the top of the stack; and peek, which returns the element on the top of the stack but does not remove it. The linked list actually makes for a great backing container for a stack. If we go turn to the whiteboard, you can see what I mean. Suppose for a moment that we were imagining a stack in our heads, like a stack of plates, where every time we want to add on plates, we add it on top of the highest plate that's currently on the stack. And when we remove plates from the stack, we do it from the top first rather than from the bottom. We use the operations push, peek, and pop to add, examine, and remove from the stack. We've talked about how the linked list is fairly efficient at being manipulated in terms of additions and removals. Here, we can implement this stack interface, the behaviors of push, peek, and pop, on the linked list very naturally. Suppose for a moment that this was our linked list, we had some number of nodes in it, and we wanted it to behave like a stack. I could write a push method that simply added to the head of the list, a peek method that simply read whatever item was contained in the head of the list, and a pop method that returned and removed this head item from the list, moving the head item forward down one element inside the linked list. So the clever thing about the stack structure is, again, it's not really a new novel way of organizing the data. It is instead a way of thinking about how we access the data. In practice, there's going to be some very interesting practical applications of using the stack. When we do language analysis, or when we walk tree structures, we're going to be using a lot of stacks. And this is actually a natural occurrence due to recursion, because underlying a program execution is something called the stack, which we'll explore in the future. In any case, I don't think this would be much of a challenge to you to write a stack class given an existing linked list class, so this is actually one of the bonus items you can do on your next project. The next structure I want to explore, also based on a linked list, is the queue. A queue is a data structure which mimics a queue in real life. It's going to support these operations: add, which inserts an element to the back of the queue; remove, or dequeue, returning and removing an element in the front of the queue; and peek, which is going to return but not remove the element currently in front of the queue. A queue, in terms of data structures, is a lot like a stack in that it's not going to necessarily enforce how we store the underlying data, but it will tell us what we do with that data and how we interact with it by having these operations add, remove, and peek. Let's take a look at how we would do that on a linked list. Check out this queue of people. They're all in line to vote, which you should certainly do if you have the chance. The people who show up first get to vote first, and the people who show up later have to wait for the people in front of them to get processed. So a queue as a structure is very much like a queue of people in line. We can build a queue based on a linked list very similarly to how we built a stack based on a linked list. Check out this example. I've got a head and a tail in my linked list, and I'll go ahead and designate the head node as the front node, so the person who showed up earliest inside of the queue. Then if I want to add members to the queue, somebody showing up at the door and going onto the back of the line, I can add them to the tail, which represents the last person in line so far. This is pretty easily doable. If I have a reference to the tail, I'll just go ahead and update that real reference and create a new node for this new person. Then if I want to peek the item at the head of the queue, I'll just go look at whatever values inside head. And if I want to remove the item at the head of the queue, then I'll just move the head pointer forwards and garbage collect the element in the very beginning. So very much like how we took the linked list and added some wrapper methods to make it like a stack, we can do the same thing with a queue. Here, all we've done is we've taken an existing structure that we know and understand, and we've added some methods such that the behavior of the structure is very specific, and we're going to interact with the underlying structure in a very specific way as defined by how the queue should behave. Once again, I think the queue is a pretty fun little exercise that you'll get to do when you have access to a linked list, so this will be yet another one of those bonus points opportunities that you can get when you work on your next project. Okay, so those are two structures you can build off the linked list. Now let's go talk about this doubly linked list, a structure that I've been teasing a lot for the last couple of lectures. And the doubly linked list is going to expand on the notion of a singly linked list by adding a reference to the previous node for every node in the list. If you remember the node class, all we had was a payload and a next reference that points to this node's successor. This new double node is going to have this additional previous field. Here I've said double node extends node, such that it's going to have the payload and the next field still. In addition to those fields, the double node will have a pointer to the predecessor of the current node. I've gone ahead and added some convenient constructors that you can optionally use, where you can define the payload and the node's neighbors. You can already start to think about the added complexity that the doubly linked list has over the singly linked list. If you're trying to push on additional items to either side of the doubly linked list, you have to update more than just one reference. You have to update two references. You have to update the reference of the new node being inserted to point forward or back to its predecessor or successor, and then you have to update its immediate neighbor to point to this new node you've just created. Similarly, when manipulating the linked list, perhaps by removing or adding items into the middle of the linked list, you have twice as many pointers that need to be updated. If you try to insert an element, then you have to rewire both neighboring items such that they're going to point correctly towards this new element that's being inserted. Similarly, if you remove from a doubly linked list, you're going to have to rewire its neighbors to point to each other rather than the element that's being removed. Let's visualize that on the whiteboard. We've got our class node, which is the same thing as the original node that just had a next and payload field, but we'll also throw in a previous field. We can draw that out by having these little class instances having three elements, the previous, payload, and next, and we'll have it such that the next field, of course, points to the successor, and the previous field points back to the predecessor. If we have a head or a tail node inside of a doubly linked list, we will set the predecessor and the successor to be null for both of those respectively. Despite the added complexity of the doubly linked list and the additional references that we have to deal with, what we'll find though is that the performance of all the operations on a typical linked list are going to be the same. We talked about how inserting into the middle of the list when we were aware of the neighboring nodes was going to be an O of 1 operation because all we had to do was rewire the pointers such that that newly inserted node became the node in the place at the index we're trying to insert to. We didn't have to shift a whole bunch of elements around because the nature of just rewiring the nearby pointers causes the successor and predecessor elements to be in the right place. It's going to take a little bit more work on your part to actually wire up those pointers correctly, but the computation cost of actually performing that action of insertion or removal is not going to scale up relative to the number of elements in the list. It's still going to be constant time. Same thing goes for appending to either side. Yes, we have to go update one more reference than we did before, but the act of updating that reference is not something that gets more expensive as the list grows bigger. Instead, it's going to be just as fast as it was in the original linked list, constant time, because we really only have to do a constant amount of operations to get that list to be changed. Perhaps you figured it out already. The doubly linked list is going to be your project 2 for this class. It's one of my favorite projects of this class because it really makes you think hard about how these structures behave underneath. You will encounter a lot of null pointer exceptions. This is going to hit you pretty hard, I think, because there's a lot of circumstances where sometimes you might forget to update a reference somewhere, and there's maybe little edge cases that you didn't think about. Again, I really recommend you download these class notes, try out step-by-step debugging to explore the behavior of the methods we implemented so far, and try out some of the algorithms that I demonstrated to you today so that you can get more comfortable working with linked lists and references. I'm going to post a Project 2 briefing video, just as I have for the previous projects, so I'll talk to you there when you're ready to go over Project 2. Okay, that's all I've got for today. Thank you for listening, and I'll talk to you next time.